This is actually last lecture in the area of packaging. Of course, tomorrow you will have, and also on Saturday, more lectures around different food processes. So this topic is about physical properties. Although it says physical properties of packaging material, if not all, many of these physical properties we are going to cover here, they are relevant to food materials as well. Can you think of what physical property we would be talking? Like a thermal properties, specific heat, thermal conductivity, diffusivity. Mechanical properties, optical properties, electrical properties. Why we need to study property for packaging material? Because we're not processing packaging, we are processing food. Why we need all these properties for packaging material?
It undergoes all these conditions.
So package can also go a lot of different processing conditions, especially in package processing. What else? What else?
Transportation.
Transportation, good.
Transportation, storage. Selectivity for a particular food.
Yeah, selection of packaging material for selection, yeah, for given food product. What else?
It should not undergo any chemical reaction with the food.
Yeah, we are focusing on physical properties, so we are not focusing on more chemical properties.
That is going to act as a protective layer to the food from the time till we use it, the entire stage.
Okay. You see, as you are processing the food, then you need properties of food, right? Because you are supplying energy. You want to see the behavior against energy. How does it behave? That energy could be mechanical, electrical, thermal energy, depending upon the processes we use. For packaging materials, initially it is just material, right? But then this material you convert into package, right? So if this plastic, where do we get this plastic? So petrochemical industry, they would polymerize the monomers and convert into resins. So these are the small beads, they look like sugar, white crystals. Of course, they are amorphous, they are not crystalline material. And then you take this material and convert into films or make trays, tubs, bottles, right? So actually you are giving a shape, to this. So that also goes through a process. Could be extrusion process, could be blown film. You melt the polymer, apply a high pressure air and allow it to form a bottle or a big bubble, and then you can form a film, you can form a bottle, or you do thermoforming. You take the plastic sheet, so you take this resin polymer, first make the plastic sheet through the extrusion process, and then from the sheet you do thermoforming. You would have a mold, and then you heat the polymer very close to melting temperature, but you don't want it to melt. You want to make it a bit soft. And then you apply a mechanical pressure, so you would have a mold, and then it can take a shape of that mold, right? So you are doing one other way processing of this polymer, right, to form a package. And in order to do that, you have the machinery, and you have the processes, and there are processing conditions. And then knowing the physical property, it will help you to select that processing condition. For example, yesterday we were looking at the sealing of the film, right? And initially when he was trying, it was not sealing because the element was not hot enough to melt the polymer, right? And we just tried one polymer. Maybe we have different polymers, right? And different polymers has different melting point or different softening point temperatures, right? So if you don't know, then how much heat you provide to the element so that is going to soften that your polymer, and then you apply a mechanical pressure and then form a seal, right? So that softening temperature is a physical property of that polymer. So with this regard, all these physical property one or other way are useful either to fabricate the packages from this polymer, or these fabricated packages go through the transportation, so we should know. And also these fabricated packages can also go through thermal processing or high pressure processing or UV processing, because you can do in-package processing. You package the food in those packages and then subject it to processing. So when you want to design these processes, then you would need the knowledge of these physical properties. Okay? So let's go and look at these properties. Yeah, so these properties are basically observable characteristics. They define the state of material and behavior under physical stresses, and these physical stresses could be thermal, electrical, mechanical, and so on. Of course, we are not looking at any change in material's chemical structure, okay, because we are looking only physical properties, not the chemical properties. And this is needed, as I said, manufacturing and uses of packages. So the class of property which we will be looking in this lecture are thermal, electromagnetic, mechanical, and diffusion, right? Why thermal property would be important? Because you are doing the fabrication of that package, you need heat to transform them from a resin into either film or tray or bottle. So all kinds of thermal property you would need. Even if you form a package, you put the food in it, and if you're doing conventional thermal processing or microwave processing, then again you need a thermal property, because if the polymer you are using for food packaging can melt at 110 degrees C, but your thermal processing conditions are 121.1 degrees C, then this polymer is not suitable. For example, most of the polyethylene, they have melting temperature around 100 degrees C. So any food which is sterilized goes through in-package sterilized process, then you don't want to use polyethylene as one of the packaging material for food. You want to use polypropylene or PET, ethylene vinyl alcohol, and so on, because they can sustain the temperature of sterilization. Electromagnetic heating, why this would be important? Yeah, again in-package sterilization, because microwave is one of the processes. So you want food to absorb energy, you don't want package to absorb the energy, especially from microwave. But once food is heated, of course it's going to give heat to the package, but then you don't want whatever microwave energy we are bombarding, it is absorbed by the package, not by the food. Right? So you want to make sure that this polymer has very, very low dielectric loss factor. What other part of the electromagnetic spectrum we use within food processing? We use radio frequency, we use UV, we use infrared, we also use X-rays, we use gamma rays, not X-rays really, but gamma rays. Yeah, we use irradiation. So actually broad range of wavelength or frequency you can call we use from electromagnetic spectrum. So that's why with respect to all those frequency and wavelength, we need to know property of these polymers. What about mechanical? Mechanical strength, tensile strength. Yeah, because during handling, there could be mechanical forces coming on those packages.
From the strain and shear graphic and like a breakdown point.
Correct. So in many times, for example, when you go to grocery store, sometimes they give you your grocery in plastic bag, right? So what is happening really? It is applying the tensile forces on it, right? If it doesn't have very strong tensile strength, and if you put more weight into this, what will happen? It's going to break apart, right? So this is why we need mechanical properties of different polymers. Diffusion, this we have studied in detail. This is basically diffusion of gases or diffusion of some of the migrants or package component, right? So for all this perspective, diffusion properties are also important for all these polymeric material which are being used for the food packaging application. So look at very quickly, I'm sure most of this thermal property which we are looking at for packaging material, but they are same for the food materials, which probably, you must be doing one course on physical properties of food or engineering properties of food. Yeah, so that course has a very similar, sort of material which I'm going to cover it here. But there are some few properties which usually you do not study for food, but they are more relevant for packaging materials. So you have specific heat, which is a constitutive property. Thermal conductivity is a transport property. Thermal expansion. Why thermal expansion would be important?
So like if the plastic, whichever polymer we take packaging, if it expands when heat is there, also the thickness reduces. So therefore, how much load we put on it would vary.
Correct. So, during storage or processing, if there is expansion in that material, right? So wherever you are processing, you should account that expansion. If you don't account material expansion, then what could happen? There could be failure, right? And this material expansion is not only important in polymer, for many applications. For example, you have seen on a railway track, the rails, between two rails, there is a small gap, right? That gap reduces in the summer months because that track expands at high temperature and tries to fill that gap. If you don't give that, then this will bend, right? Or if you're holding a material between two walls, right? And if that material expands, then what will happen? It will have the stresses. Internal stresses will be generated because material is trying to expand and you are holding it. So it's almost like you have a material and applying a pressure from both sides, right? When we have this can, beverages can, like a soft drinks, as we all know that colder the temperature of soft drinks, better it tastes, right? It's extremely chill because you have very high solubility of carbon dioxide at very low temperature, right? So sometimes you must have observed that if there's a party at 5 o'clock and you didn't remember to put your cans into fridge, then what we do, we just put in a freezer. We think that it's going to cool down quickly, and it does because there's a more temperature differential, right? In freezer you have minus 18 rather than in a fridge where you have 4 or 5 degrees C. So it cools down very quickly. But in case if you forgot to remove one can, if it is left there in freezer, what will happen? It bursts. Why it bursts? Correct. So water which is there in the can, it will turn into ice, and ice is a low density than water, and it would expand. And if there's not sufficient gap into it, it's going to apply that pressure on the can and it's going to just break the seal. Or the same thing for the water bottle. So we do need to account this material expansion in the handling of packaging materials. Transition temperatures, these are, for example, melting point or crystallization point, or you have glass transition temperatures. We gave example in the morning that if the polymer is flexible at room temperature, if you happen to put in a freezer at very, very low temperature, it's going to increase the viscosity dramatically. It may be in a glassy state, and if it is in a glassy state, then you apply any mechanical sudden impact on it, it can simply break, right? So if any polymer material you want to use for freezing application, you want to make sure that it has very, very low glass transition temperature. It means that even at minus 18 degrees C, it should be flexible. If it is not flexible as minus 18 degrees C, it is very rigid. Then during the transportation or handling, if there is a sudden impact on it, it's going to break. So again, transition temperatures are important to know for those polymeric materials so that you can suitably select for refrigeration application or freezing application or room temperature application or even high temperature application. And heat of combustion. What is heat of combustion? Not required. When you heat it, it burns, then how much heat it can give you. Okay? So as you know, we discussed in the morning also, when you burn the paper or plastic, they give you heat. As they burn, combustion goes, then they give you heat. This information is useful if you are sort of trying to recycle, or trying to incinerate, these polymeric material or waste packaging, then you can recover some heat from that. Yeah, so all this property, one or other way, important in estimating the heat flux during heating, cooling, processing, whether processing of package or food processing, storage, package fabrication, and so on. So very quickly, specific heat. You all know amount of heat required to change temperature of a material of a unit mass by 1 degree. This is the formula, mathematical description. Why different materials have different CP?
Molecular lattice.
So maybe because of Q, it also depends upon thermal conductivity of the material.
Why different materials may have different CP? The different materials are made of different molecules. Could be carbon, could be hydrogen, and the molecular packing or the structure of these molecules are different. That makes the difference in CP. So they have different molar masses, and CP of amorphous solid is higher than the CP of crystalline solid. What is the difference between amorphous solids and crystalline solids?
Molecules are tightly packed in the
In crystalline solids, the molecules and atoms are arranged in very orderly fashion. There's no gap in between. But in case of amorphous material, these polymeric chains are not. These are usually large molecules, and they are not arranged in a very orderly fashion. And that's why we call them amorphous, because they are not in order. So CP of those amorphous materials tend to be higher than crystalline material, and it is giving you some range of CP for different materials normally used.
CP of amorphous should be more than, because if there will be a less idea, CP of amorphous should be lesser than, because they have more void spaces, more air is involved.
No, it's not because of the air. So tell me, what is the difference? How do you define the temperature?
Temperature is relative.
What is the definition of temperature? And what does it tell us? Measure of? Well, hotness is a very crude word. What is happening at molecular level? One material has a more temperature than the other material. Okay, so what? What is really happening?
The one with higher temperature will have higher energy. So internal energy will be higher in that, rather than in comparison with lower temperature.
And how this energy is really stored in the material? So it's not thermal. It is you characterize the temperature. Temperature is actually measure of the kinetic motions of those molecules. they are vibrating. So that vibration is proportional to the temperature you have, right? So now think about the amorphous material and think about the crystalline material. The level of vibration you can allow to have in amorphous material will be higher or crystalline material. In crystalline materials, the molecules are lightly packed, but in case of amorphous material, they are loosely packed. So you will require more heat for amorphous material in order to induce that vibration. To have the same change of temperature, you need more energy. Okay, so that's why Cp for those amorphous materials is higher. So here's showing you stainless steel, glass, aluminum, LDPE, and wood material. So if you really see stainless steel or metals, they have the lower specific heat than wood, which is also polymer, cellulose, made of cellulose. Cellulose has a polymeric structure, and LDPE. Okay, and then you see that those polymeric material have the higher Cp. Thermal conductivity, this also we talked yesterday, this is the ability of material to transfer heat by conduction mode of heat transfer. You describe using Fourier law of heat conduction, and mathematically you can describe as a Q is equal to minus K A delta T over dx, and K is the one here, thermal conductivity. And conductivity depends upon structure as well as temperature. So higher the temperature, higher the thermal conductivity. Even for a specific heat, higher the temperature, higher the specific heat. So if higher the temperature, higher the specific heat, what does it mean? So let's say you have material at 20 degrees C, you want to add some amount of energy to raise its temperature from 20 to 25, right? So you need to add some energy. How much energy you need to add? Q is equal to mCp delta T, which is 5, right? Now if you want to increase the temperature of the material from 25 to 30, we are saying you need to add more energy than what you added previously to increase the temperature from 20 to 25, because higher the temperature, higher the Cp. So in order to have storage of that energy or to have that level of vibration of those molecules, you need to add much more energy. And thermal conductivity for gases, as you all know, is very low. Why it is low?
Because the
Molecules are far apart, so they really had to travel and touch each other to give the energy. In case of non-metals, the heat transfer is by lattice vibration, and that's also known as a phonons. And in case of metals, the heat conduction happen very similar manner as the transfer of electrons, as happened in the case of electricity transfer through metals. Because you have free electrons, they can travel around, so they conduct the electricity, current. At the same time, they also participate in heat transfer. This is showing you the thermal conductivity of different packaging materials. So as you can see that metals have very, very high thermal conductivity, and as you can see that many of the polymer have low thermal conductivity, and in fact this is expanded PS. You know what is expanded PS? Polystyrene, right? This we use as a cooler, right? Like an ice box, simply because it has a lot of air entrapped, which has a very, very low thermal conductivity. So this expanded polystyrene is actually 95% air entrapped between the polymer, and that also gives you very low thermal conductivity. Thermal expansion could be in the form of linear, which is one-dimensional expansion, but you could have the volumetric expansion, which accounts for expansion in all three directions. So this is how you would define coefficient of linear expansion. L is the expansion as a result of change in temperature, that's a delta T, and alpha is the coefficient of thermal expansion. It's actually, in this case, linear expansion, and L is showing the initial length. So if you know the expansion coefficient and whatever change in the temperature happens during storage or processing, you can find how much will be the linear change in the dimension. And same thing, same concept for the volumetric expansion. It is expansion in all three dimensions, so volume change. And in general, alpha, which is a linear expansion, is 1/3 of the volumetric expansion, which makes sense. Volumetric is three-dimensional expansion. So it is important because it could be shrinkage or expansion in a constrained space. So it is very important. We gave some example where these, thermal expansion would be important. And as you can see here, different material have different level of expansion. Actually, polypropylene has actually 2 orders of magnitude more expansion compared to ceramics and wood, right? So you really need to know this number. Otherwise, during processing, if you do not account, then you may have failure in the material. Other important thing for packaging material is the tolerable thermal range. What does tolerable thermal range means? For the lowest limit is the temperature at which the material shows maximum fragility affordable during commercial distribution. That's what I was giving example, that if you have a polymer, if you keep on lowering the temperature, at some point the material, if it becomes very fragile and which can break during commercial distribution, then that's the lowest limit, because you don't want to go lower than that because it's going to fail, right? So for example, a polymer which can turn from flexible state or rubbery state to glassy state at -5 degrees C, right? Then you don't want to cool down, and if it turns very rigid and glassy structure at -5 degrees C, and during transportation, if there is a possibility of breaking of that container, then you don't want to cool that material or that polymer to the -5. So you want to have -7, -8, -10, but not -5. So that's their lowest limit. So you want to maintain the temperature of this packaging material slightly above than the lowest limit, because at lowest limit it may have the possibility of damage or breakage. And the highest limit of temperature is that it begins to cause physical distortion. If you keep on increasing temperature, what will happen? It starts become softening, and then eventually it could melt, and it can affect its performance. And in fact, after a certain temperature, you may start having chemical changes in that material, right? So for every polymer, there will be range, 10 to 80 degree, -5 to 50 degree, or -18 to +200. So that tolerable limit, you should use material within that. You should, if you have application where this temperature goes beyond the tolerable limit, then you are not going to use this polymer. You are going to use different polymer which has a higher tolerable thermal range. So this is more related to this application final package rather than the raw material, because you are looking at tolerable limit within the package, not really in the raw material. So this is lowest and highest limit for some of the materials. So stainless steel -45 to 600 and so on. And glass, of course, can be very, very low. Aluminum, fluoropolymer, and so on. So you have different polymers. So for example, if you have PVC, you don't want to use PVC less than 15 degrees C or more than 85 degrees C. So for example, if you need to select a polymer for freezing application, you will not select this because freezing is at -18. So you may be selecting probably some of these polymers. You will not select also this nylon, which is polyamide, because it can sustain up to -10 degrees C. Transition temperatures. Transition, it could be transition of state or transition of phase. Phase we are referring going from liquid to solid or solid to liquid or liquid to vapor. But the state change we are looking is a glassy state or rubbery state, right? Because in a glassy state it would appear to be solid, and rubbery state it will have a sufficient flowability. So these transition temperatures are also very important for polymers, because if you have a container which you want to maintain it to solid state, you don't want it to go through glass transition, because if it goes through the glass transition, then it will have a sufficient flowability, and then it can deform, right? So if you have a polymer which you are going to use for thermal processing application, in thermal processing application, what would be the processing temperature? 121 degrees C, or sometimes it could be even few degree higher, right? So you don't want this material at that temperature goes through state or phase transitions, right? Because if the package goes through state and phase transition, then what will happen? Small pressure, it will have a deformation, right? So you don't want that. So that's why it is important. So this transition temperature we are talking about melting, glass transition, or crystallization. So that depends upon degree of crystallization. So if you, as we know that almost all the polymer, they are semi-crystalline in nature. It means partly they are crystalline and partly they are amorphous, right? So there these transition temperature depends upon what level of crystallization or crystallinity is there in that polymer. And you can do different level of polymerization. That's why within polyethylene, you will have different grades. It's the same polymer, but the degree of polymerization is different, molecular weight is different. Hence, you will have this different transition temperatures. So if you have the crystalline material, if you heat, as long as it is solid, then it would maintain its stiffness, but at some point when it starts melting, then the stiffness will suddenly drop. But the amorphous material which goes through the glass transition, its stiffness changes very gradually. Okay, so how does this information is important? So if you have a crystalline material, for example, ice is a crystalline material, right? If you have an ice at minus 18 degrees C, if you provide the heat, what will happen? Its temperature will increase from minus 18, it could be minus 15, minus 12, minus 9, minus 6, minus 3, then it will reach to 0 degree ice. So ice will be at 0 degree, and if you apply some more heat, what will happen? It will simply melt, right? But if you have this polymer, and when it melts, it has become liquid, low viscosity liquid. But if you have plastic, which appears to be solid at room temperature, if you provide some heat, what you will see, slowly it becomes soft, and suddenly you would see, not suddenly, slowly you will see this soft material become very high viscosity, extremely high viscosity liquid, and then slowly you would see that the viscosity is going down and getting thinner and thinner as you're increasing. So there is no sudden change like in crystalline material. So crystalline material will be solid, then at some temperature it will simply melt and you have a liquid. But then for amorphous material, it will have gradual change in the viscosity, and if the gradual change in viscosity is a gradual change in its stiffness or mechanical property. But in case of a crystalline material, you will have sudden change in its mechanical properties. So this table is showing you melting temperature and glass transition temperature of some of these polymers. So then you can see that the range. So far in case of a glass and steel, as you see, especially steel, you see very high melting temperature. Why the glass doesn't have melting temperature? Because glass is amorphous. For amorphous, you have glass transition temperature, not the melting temperature. But for polymer, you have both melting temperature and glass transition temperature most of the time. Why? Because polymers are semi-crystalline. So partly they are crystalline, partly amorphous. So the crystalline part would melt and amorphous part will go through the glass transition. So you can see this range for different materials in terms of the melting point and glass transition temperature. So based on this information, it can help you whether you want to use this polymer for freezing application, or refrigeration application, or pasteurization application, or thermal processing application, which is like sterilization application. Heat of combustion is the amount of energy release from the total combustion of a material. It's basically important in terms of the energy recovery. Rather than throwing that material, you want to recover some energy. And that happens with two materials, cellulose-based material and plastic. So this is giving you the heat of combustion. So polyester has 33 megajoules per kilogram, PP 43, and so on. So which material can give you the most heat? Polypropylene is 43. So polypropylene burning as good as you're burning the oil, right? So this is how you can, design your processes, saying, hey, if I had to buy 1 ton waste of cellulose or wood, or if I have 1 ton waste of polypropylene, and if you have to pay for that waste because your plant is engaged in the energy recovery, right? So for which material you will pay more? Polypropylene, because it can give you so much more energy than these materials.
So it can produce some toxic gases as well.
That's true. It can produce some of the hazardous compound, but your plant would be, if we know that, then we can design a system where we can trap, right? Many industries, they produce a lot of pollutant, and if we don't have a control, they get into atmosphere, they get into our water supply, they can get into the groundwater. But then if you take appropriate precaution, there are guidelines, and then you can entrap those all hazardous compound, and then you can take care of those compounds. So they do that actually. Many of the medical packaging, right, they have some of these polymers used. For example, those plastic bags in which you would collect, you have the glucose, right, as IV fluid, right, or sometimes you have blood transfusion. So these are the polymeric bags. So you don't really throw them in the environment just like that. You really, in most cases, this polymer packaging which is used for medical application, it goes through actually incineration or combustion. Electromagnetic properties, well, the packaging material could go through electromagnetic field of different frequency and wavelengths. So you want to see that behavior under the electromagnetic radiation, and many of you did give example, could be X-ray, gamma rays, UV, visible, infrared, microwave, radio waves, and so on. And these are some of the application. These gamma rays for sterilization, X-ray for thickness measurement, UV for food protection. There is going to be a lecture on UVC light tomorrow, so you will see that you can do surface sanitization of food product using UVC light, but you can also do in-package processing. So first you package your meat slices or cucumber, whatever surface you want to sanitize with UVC light, and then you subject to UVC light after packaging. What would be the advantage of in-package processing compared to direct processing? Because if you do in-package processing, if the surface is sanitized, the product is sanitized, and if it's already packaged, there's no chance of recontamination. But if you do in an open, by the time you package from the environment, it can still pick up the bacteria and can again get contaminated. So again, you want to make sure that this package is permeable to UVC light so that it can reach to the food surface and sanitize the food surface. So visible light is important in terms of the transparency. If visible light cannot pass through it, then you will not see what is the other side of the package. Infrared, they do a lot of research here, infrared heating, microwave, as all you know, for pasteurization and sterilization. The optical property is very clear that you want light to pass through it so that you can see it. So it is for clarity, and it could be transparent or translucent. And in some film you can have a haze, which is basically cloudiness or milkiness, and that could come because of the imperfection at the surfaces when you are making these packages, either films or trays. And this haze is also affected by the crystallinity or aggregation of crystals in those polymers when you are doing the polymerization process of those polymer. Yeah, so all this, package property, whether it's during polymerization of those polymers or during processing, which means you're converting these polymers into film or trays or bottles, you could have some imperfection, and that can change the optical property. And it is important because you want to clearly see what is inside. So those are optical property you can characterize in terms of the transmittance, reflectance. What is the difference between transmittance and reflectance? So how much light is passing through and how much light is reflecting. If too much light reflects, then what will happen? You will not see what is inside. It's like if it's a very glossy surface, then a lot of light reflects, so it appears shiny, the surface itself, but you don't see what is inside, right? So these are important depending upon what product you have inside, what kind of a transmittance or reflectance want on that surface based on the application of that packaging material. Other than transmittance and reflectance, what you have, if the light strikes on the surface, well, that refraction also actually in a way transmittance, although it's in that case it just deflects the light. Absorptions, yeah. You also don't want the material to, this polymer to absorb a lot of light, because again you won't be able to see through. Yeah, glasses where you have a lot of reflection, then that surface will start appearing like a mirror if a lot of light is reflected. So you don't want in some cases, because you want it to see through, but in some cases you want really shiny. You are not, for example, I have seen sometimes these gift wrap for candies, you have in a basket and you wrap around with very glossy film, because that's the importance there is that how shiny that film is rather than what is inside that basket. Yeah. So depending upon the application, you can develop the packaging or select the packaging which has different amount of transmittance or reflectance of light. Yeah, and this happens, this transmittance, reflectance, based on the refractive index of the material, density different between amorphous and crystalline phase, because in polymer, as I said, you always have a structure which is semi-crystalline. The part of the polymer is crystalline and part of the polymer is amorphous. So the difference, the ratio between amorphous phase and crystalline phase can give you different amount of refractive index, different amount of transmittance and reflectance. So when you are designing the film or fabricating the film, if you have a specific need that you want this level of transmittance, you want extremely clear film, then you would adjust your amorphousness or crystalline phase in your polymer accordingly. So all this optical property knowledge is important depending upon the application, what level of optical property you want, and then you go back and tell polymer engineers that do this kind of a processing, that because we want very clear film or not very clear film, so they can adjust their processing condition to get you the film or packaging material with the desired optical property. This is the mechanical property. We saw this instrument yesterday, texture analyzer. So you would have strain versus stress. This is strain, you are getting the change in the length over the original length, and stress is the force over area. And then this is how most polymeric material, if not all, would have this is a typical curve, and this from slope you can find the Young's modulus, which is the stress over a strain. So this is a linear range. If you take a slope, that will give you Young's modulus, and yield strength is the one where you start seeing the deformation, without any further force applied. So up to here, you're applying a force, you see the change in the dimension. But at this level, even if you don't apply force, you keep seeing the elongation or change in the length, and at some point it's just going to break, and where it breaks you have the tensile strength. Yeah, so these are some of the important parameters: tensile strength, yield strength, elongation, Young's modulus. These kind of parameter you will measure for your polymeric film or whatever polymeric material you have, and then it will help you to compare the mechanical strength from one material to another material. And once you compare the strength, then depending upon the application, if there are a lot of mechanical vibration during handling or transport or storage or during processing, then you will select appropriate packaging material to sustain that level of mechanical stresses. So these are some of the strain stress curve for different polymeric material. I think, yeah. And then you characterize soft and weak, or hard and brittle, hard and strong, depending upon how much you have stress that material can take and how much elongation it can have. So based on that you will characterize whether it's a strong material or soft material or weak material or tough material or hard material and so on. And as I was mentioning in one of the previous classes, that whenever you do this property measurement, like you do the composition measurement like a food analysis, you have AOAC standards protocol. In a similar manner, many of these mechanical property, when you measure for these polymeric materials, you have some code that what would be the sample size, how much force you will apply, how you will apply, and how you will measure the elongation or change in the length. Right? So there are particular protocols you follow. So these are the one. ASTM is American, BS is the British. So these are the code. So if you go in those books, you just find for this code and it give you entire protocol how you would measure. So bursting strength is the resistance to pressure applied at right angle. Sometimes we do burst testing ourselves. Have you done in not really polymeric material but any other material? Sometimes we take a balloon and we hit at the right angle and it bursts. Or sometimes we have this brown bags, paper bags. We just blow the air, hold it, and apply some pressure at the right angle and see when it bursts. Right? So this is how you would do the experiment. You blow up, have the air, and apply the force at perpendicular direction, and amount of force required to burst. That is this bursting strength. And impact, which is different than the burst, is that in case of impact, you apply sudden pressure or shock. So for example, if you take a glass, if you put a probe on it and start applying the pressure, it will break after very, very high amount of pressure or force, right? But if you have the impact, right, which is the sudden force, with a very small force, it will break. Right? So yeah, so you characterize the mechanical property differently, whether this force is a steady state force or the dynamic force or the sudden force, and based on that they can give you different properties. Tear strength is the energy required to tear. So for example, have you seen paper? Very small amount of force is required. You make a little bit notch, apply small force, then you can have the tear. In a similar manner, some polymer, they are very easy to tear, while other polymers are not. And I'm sure you must have experienced this. Sometimes we have these small pouches. For example, in a hotel where I'm staying, to make tea or coffee, they have this milk powder in a small pouch. And I had to really struggle to really open, even though there is a notch. So this has a aluminum layer, aluminum foil, but aluminum foil you cannot seal. So inside for sealing, they provide the polymeric film that can help in sealing. But this polymeric film has a very high tear strength, so it will not tear very easily, right? So I had to really, and if you have apply very high, then if you shake a little bit, the powder just falls. So it's a bad packaging, bad design. They could select a film or polymer which has a good sealability but has a low tear strength, right? So you can easily tear. So many of these pouches, sometimes chips bag, And many of these, sometimes we really struggle in order to open that, simply because the polymeric films which are using in that, they have very high very high tear strength. So the knowledge of this tear strength in different polymer material will help you to select for appropriate application. Stiffness is that resistance to distortion. Sometimes we try to fold. So how flexible that is. So that's the stiffness. And crease is, or flex resistance is that you do multiple folding. It's just not the bending, but it's the multiple folding. So sometimes we take a paper, we fold once, fold second time, third time, have multiple folding. So that multiple folding could happen also in case of polymeric films. So some have lot of resistance to multiple folding. You can fold one or twice, but then you cannot have multiple folding, while other films will allow you multiple folding. So again, depending upon the situation, you would select the appropriate film. Coefficient of friction, it is defined as the ease with which surface of one material will slide over another material. How this information would be important? Produce laminates. See, in case of a laminates, you're just bringing two layer and laminating. But coefficient of friction, did we saw yesterday? I think when I was, we didn't show you guys. So, so when one surface slides over another surface, right? You required some force, right, in order to slide one surface over other surface. And so that's the friction, right? Do you think friction is important? If we didn't have a friction on Earth's surface, what will happen? We won't be able to walk, we will be sliding, right? So some friction is important, but if it is a lot of friction, then it will require a lot of energy to move things on one surface over another. So when they design the tire for our cars or our two-wheelers, they have to come somewhere in between. If they have very large friction, then it will require a lot of forces to ride the bike, a bicycle. But if it's very little friction, then it will be just sliding. Then it will be very easy to stop. We are able to stop only because there is a friction. So in the same manner, we need to understand the frictional properties of these materials, because in industry, there's a lot of automation. So one surface slides on another surface. So for example, if you have glass bottle, let's say, it is being automatically filled with the milk or juice, right? And after filling, it's going to fall on the belt, and the belt is conveying. And at the other end, you will collect it and put in a big carton, right? So if, imagine the glass bottle is being filled and drops on your conveying belt, which is made of polymer. These are mostly plastic belts. If there was no friction, then once bottle will fall, if there was no friction, it will start rolling, right? Because of the friction, it will just stay there where it is going to fall. So again, the frictional property of this would be important as a consideration for designing the conveying system. So like that, it could be many other applications where one material is sliding, or one surface, which is the glass surface or metal surface or cellular surface, is sliding over polymer. And depending upon this coefficient of friction on one polymer or other polymers, it will help you to select appropriate polymer for making those conveying system. Blocking is the tendency of two adjacent layer film to stick together, right? Sometimes you would see these films, so they have so much static energy that they come and join together. Just you want to really take it apart, but they just come and stick together. So depending upon, again, application, sometimes you don't want, blocking of these polymers, polymeric films. Shrinkage is basically change in dimension, and that just could happen due to heat, moisture, or creep. You know what is creep?
Creep is a deformation due to frequent knots or loading all the times, but at an intervals. like we have creep in bridges.
Any other example? Did you do in a mechanical property measurement creep? So creep is you apply a small amount of force but for very long duration of time, and under that some material could fail even though they are very strong. This phenomena was observed. For example, you have a ceiling fan, they are stuck and hanging with one rod, right? Well, ceiling fan is not very heavy, so if you take that rod, you try to pull, it feels very strong, but it has happened cases where it is hanging for 30 years and it will suddenly fall. So the small amount of force applied for a long period of time and then material could fail. And parallel to this analogy is with the moving object, which we call as the fatigue test. So there the object is moving, small forces, but it's moving continuously, and that is applied. For example, we have motorcycle or car where you have the axle, they keep rotating, right? But let's say the engines, right? They keep working. Sometimes these engines works 24/7, right? The amount of forces being applied are very small, but these forces are being applied for continuously for a long period of time, and then material could fail. So it is interesting, this material, when you apply steady state force, they appear to be extremely strong, but then the small amount of force, long period of time, and they break. So depending upon, again, application, if this polymeric material is under creep, then you want to find out the creep strength. I could do the creep test to make sure that it would not fail. So this is what I have for material properties. If you have any question, I'll be happy to answer. So if you have any question about this topic or whatever topics we have covered, or you have anything about food processing, engineering, or food technology, if I know, then I will be happy to answer your question.
So slide 22.
Sure. Yeah.
So what's the difference between strong and tough?
Well, actually, they both are referring to, at least tough, I know it is referring to that it breaks after a very long elongation, and hard is referring to actually the stresses. So, yeah, one is along to stresses and one is along to elongation. These are not really true to the scale, actually.
So I'm asking the literal difference between strong and tough. What is the difference between the word strong and the tough, the terms which we are using?
A good question. Let me see, what do I see here? I really do not see much difference here. I don't know why they use. Soft and hard is definitely based on the, as you can see, there's a little bit of scale, this and this. The forces applied for the yield point, this is higher than this. But in both cases, also, the elongation is quite long. The difference could be maybe the distance at which you are seeing this deformation happening. I'm not sure. I really need to see why they're really calling difference. That's a good question. Do you see any difference between these two curves?
So this strain stress graph is second puncture has more slope in the strong objects but has lesser slope in the tough object. The second impression which we
This one?
tough.
This slope you're talking about?
Second.
The linear region?
No. After yield point. Means no. The first peak after first peak.
This peak?
After first peak, the slope of stress strain curve is more in strong objects and lesser in tough objects.
This slope.
After first peak.
See, it says hard and strong here also.
But in strong objects, the objects suddenly goes under elongations whenever the force applied. But in tough, it is taking time, sir. Not that much easy.
So where is the time here in this?
Time means with applied force.
No, how would you explain between these two?
Once you started applying the force, the tough object started its elongation, strength changing. But in tough objects, it is not that much, sir. It's bearing some load initially.
So you are referring to this
Yeah,
slope?
yeah, sir. Yeah.
Okay. Well, so this could be an interpretation, if you're right. I need to see. So soft and hard is based on this height, the force, and then the strong and tough is based on the distance from here and when you start having this elongation. So in this case, this distance is lower, and in this case, this distance is more. But we can verify from the book that that's what it is really. Any other question?
I had a question. Not related to the subject. Here we talk of innovative food processing technologies in which we include high pressure processing or microwave or next like UV or something processed. This is so means somehow innovative for us because we don't use as in India. What kind of innovative food processing technology you are working over there?
So even in from US perspective or European perspective, these are relatively new. So if you see the heat processing, it has been there at the time of Nicolas Appert, or even before that, we were using heat as a medium for cooking as well as preservation processing, right? The application of high pressure, pulse electric field, UVC light, what else? Ultrasound, or even magnet. All this new physical stresses is relatively recent, last 25 to 30 years at the most. Universities have been doing a lot of research, and out of that, we had very little commercial success. So in terms of the commercial product available in the market, in Europe or Japan or US, there's a limited number of products from high pressure processing technologies. And PEF, pulse electric field, we are not using yet for any preservation and processing purposes. But I know in US, a company named Simplot, which makes a lot of French fries for the rest of the world, and McDonald's buys from them. They are using the peeling of the skin from the potato. They subject it to pulse electric field that loosens the skin, and then it's easy to remove. There is some research where they show extraction of bioactive compound or some of the bioactive molecules from plant material. Usually we use organic solvents, right, for the extraction of these molecules. But then this extraction you can accelerate or improve the yield by applying sometimes ultrasound, sometimes even microwave, high pressure, pulse electric field, and so on. But as a process product coming from these technologies, we have not many. In terms of the UVC light, again, for food application is a bit limited. For purification of air or sanitization of air in the room, industrial rooms, storage for apples or different food commodity, they have a lot of UVC light in the room. Everybody goes out, they close the door and sanitize the air, or they can sanitize the air separately and then they can pump that sanitized air. The water, industrial water, for that sanitization of that water, they use UVC light. They use for application for packaging surface sanitization. For example, aseptic processing and packaging, if you had to sterilize the surface, many times if it's, let's say, paper base, yeah, so rather than using steam or hot water, then they use hydrogen peroxide, or sometimes they use UVC light as well. So there have been some success in terms of use of this application, but in comparison to the amount of processing we do using heat, still that fraction is like a total volume is in terms of the fractions. So still a lot of challenges, technical challenges, sometimes the cost, sometimes energy efficiency. Because of all these challenges, these people still keep on working. So even for the Western world, these are still advanced and emerging technologies.
3D printing of foods is another aspect which you guys are working on.
So what kind of views you have about 3D printing of food?
Pizza is printed using 3D printing.
So you see on that YouTube, right?
YouTube, there are some companies which are making 3D printers of food for sugar candies, cake and pastries.
Yeah, so they are at very early stage of their development, and people present all kinds of argument for that 3D printing. Yeah, so they have started using and to see what kind of product they can formulate from the 3D printing. So initially they are looking at maybe at home when you want to bake the cake or want to prepare the candy, and you can create all kinds of shapes, very intricate shapes using 3D printing. But we need to see, how different product we can produce and what is the perception from the consumer point of view. Yeah, so this is one of the emerging, sort of technology you could call a method of some food preparation. So this is more like a food preparation rather than preservation and kind of proper processing.
This can solve the problem of NASA people's 3D printing of food.
Well, they had to take all the ingredient. It's just the printing, but all the ingredient you had to take it from here.
That they can do if they need 5 years of shelf life. They can definitely do that. Anyway, they will have to carry all the foods.
See, again, you don't print the meat. You are, you're not doing basic printing of vegetables, fruit, and meat. We are not born to eat, only chocolates and candies, right, which 3D printing does so far. So, well, if it is developed to that level, possibly they can take also to the Mars.
Sir, nowadays people are aware of those preservatives used in food processing applications. So what is your comment on those additives? Means what I mean to say is people are going towards organic whatever food we are consuming. Yeah, they want to eat raw vegetables instead of processing, because processing stuff will be having some kind of preservatives and chemicals. So people are aware of that. And what is your comment?
Yeah, well, I can make a little bit comment. Again, I'm not really food chemist who understand the chemistry of these preservative, but people put all kinds of argument. So in principle, it appears very logical that we do not want any synthetic preservatives, right? Chemical preservative. But many times you have a very natural preservative, right? Or sometimes chemists will argue, well, even though they are synthetic, but many times their structure is very close to the natural one, right? For example, vitamins, right? We get supplements in the market, right? You can buy vitamin C tablets, right? Where do this vitamin C comes in those bottles? They're not extracting from mango or orange or lemon. The cost of extraction would be enormous. So they fabricating in the lab and the plant, right? Which has exactly same chemical structure as a natural vitamin C. So then what is the natural, what is synthetic? It has the same chemistry, absolutely same chemistry. So now, how would you argue? Is the synthetic is not good? So I'm not really advocating, chemical preservatives. Yes, but consumer can really drive the industry to get rid of chemical preservatives. So if the consumer don't like, then food industry will find other means. For example, they can.
People use processed food in US. That's what I'm asking.
Yeah, today we use in US, tomorrow you're going to use in India. If your generation doesn't use, the coming generation is going to use. The way life is changing, the change is kind of unstoppable, right? Our parents, grandparents didn't use a smartphone. We probably cannot live. I don't think your generation can ever live without smartphones. So of course you're selecting, right now like that, you're not selecting the processed food, but the way our lifestyle is headed, I mean, I cannot say anything for guarantee, but the way it looks, I mean, what processed food we had in India 30 years ago and what we have today, there is a difference. So yeah, but you are right. In America and Europe, they are looking clean label. That's the term which has become very popular, where you want package which is bio-based, green packaging. You want food which are organically grown, and you want also all natural, so no synthetic preservatives. So that's really trained, and slowly, where possible, food industry is trying to replace with the natural. Many places wherever it is working, and many places where it's economic, right? Because many times we just demand, but we don't want to pay, right? Then it's a problem for food industry, right? So wherever it's possible, they are doing it. And it may happen that after 10, 15 years, we get rid of all synthetic chemicals or preservatives which we are adding in a food, and then we may have all natural one. People have argument for bio-based packaging. So some people do what they call life cycle assessment. Have you heard word LCA? So sometimes we look the analysis from one angle. Oh, this plastic is not biodegradable, so it's bad, right? But some people have done comparatively studies that bio-based packaging comes from where? Plant. Well, plants are not free. We are growing it, so you need a land, and this land is not fertile forever, right? More you produce, you're damaging the land also. So that you're not counting, just you're thinking it's a bio-base, so it's good. What about the water? We need water to grow plant. Well, water is not free. Today we have a lot of water, but with time we are running out of the water, good quality water also. More and water we are consuming the groundwater or the pure water, drinking water, and becoming saline, is getting into the sea. So if you just think, oh, we have a lot of land, we are going to cultivate a lot of plants, this land is not going to support forever the production of the plants, right? And so you account for that. Then you account if the bio-based packaging is a bit heavier, high density material compared to, let's say, synthetic polymer, right? Then the transport is going to cost more, right? So the energy spent to manage this bio-based material may be more, right? Just because it is biodegradable or compostable, you cannot just vote that, oh, this is the best. In order to maintain and manage that material, if you have to spend more energy, then that's not good. So you should account all the energy, everything, in order before you make any decision. So that's another argument. So yeah, but it's a good questions. People in a society, they debate, they talk, and they slowly find the solution.
In previous lectures, we heard about edible coatings and encapsulated materials used in packaging. Are there certain things which cannot be packed, or disadvantages of these materials?
So far, whatever research has been done, we have more edible coating rather than edible packaging. So bio-based coating is more commercial reality compared to edible films. You would see some sausages are wrapped the edible film, so you don't have to remove before eating the sausages. So those are really first fabricated film, and then the ground meat is filled in that, and then you have the film there outside. But as I know, there's not too many application of films, but coatings, like for example, apples, they're wax coated to avoid the moisture loss during storage. Almonds are being coated to avoid contact with the atmospheric oxygen because they contain lipids and you could have lipid oxidation. So there has been some success in terms of the edible coatings compared to edible films. And you said some microencapsulation?
Where we cannot use it, the places where we cannot use edible coatings and
Well, you can coat anything, but if it is not giving you any advantage, quality or shelf life advantage, then if the products are extremely moisture sensitive during coating, many times in terms of the coating, these polymers are dissolved in some solvent, then you spray on those material and allow solvent to evaporate, and then you form a coat there, right? So even if they do almond coating, either you can do a spray or you can dip in the solution and then remove, let's say, almond from that solution and allow it to dry. So if the solvent is water, then water will evaporate and it will form a thin film, thin coating over the almonds or walnuts. And then it is expected that it would help to protect. But if the product is extremely moisture sensitive, then if the solvent is water, then you won't be able to apply spray or dip. That's the thing I could think of it. And in terms of the encapsulation, is always we talk about macroencapsulation. So the biopolymers are very well used, protein, polysaccharides. They are using encapsulation of flavors, minerals, vitamins, some essential oils. And then this encapsulated powder, then you can incorporate in dairy product or bakery product or beverages. Yeah.
Sir, you have told about antimicrobial packaging. Why most of the antimicrobial packaging are limited to meat and meat-associated products?
Yeah, as we like meat, microbes also like meat a lot. So the microbial problem, again, I'm not a microbiologist, but as I know a little bit, microbial spoilage of animal-based product is more than the plant materials. So if you see vegetables without doing much, they can last several days, if not weeks. Fruit, even also room temperature, refrigeration temperature, they last long. But once you have meat, whether it's a chicken, poultry, or fish, or cow, beef, or whatever meat you have, after slaughter, they quickly spoil. So probably there is a need to,
What are the
try.
other products we could try this?
Well, anywhere that the microbial spoilage is great, large, then that would be economic value for antimicrobial coating to try on those products. You can try on any product, but if the product is not susceptible to microbial spoilage, it's taking 3 weeks to spoil by the time people are going to consume it, so then say, hey, there's no use of it. So wherever there is a microbial issue or more pressing issue, then you are going to try there. So that's what I could think of. The meat product, they quickly spoil. They have very, very short shelf life. And then all spoilage is due to bacteria, not because any nutrient or any other quality factor, because most of the time this raw meat you're going to cook. So that is going to impart flavor and other quality attribute. But then if the microbial load is too high, then the textural breakdown, and drip loss could happen. So to minimize that, you don't want the microbial contamination. You want to minimize as much as possible. Some of the microbes get killed or inactivated during cooking, but then you cannot depend elimination of all microbes because people may not do very thorough cooking. So you don't want the load beyond certain limit. Yeah. And definitely you don't want any pathogen. Spoilage are still okay. You definitely don't want any pathogen. So most of the time this antimicrobial is more to minimize the pathogen safety outbreaks rather than spoilage.
So, like in India, in a recent study, they told that the major losses after post-harvest is because of fruits and vegetables. Like that, what causes the major loss to the economy of US after post-harvest?
Very good question. Can anybody think of it? So when I started teaching food packaging class about 11 years ago, in textbook is also written that and European nations and American, they brag about themselves saying, oh well, in the underdeveloped countries, developing economies, 30, 40, sometimes 50% losses in post-harvest losses, fruits, vegetable, grains, and so on. And the developed economies, they are very good. They have really made use of food science, technology, and engineering to process and preserve the food, and they have only 2 to 3% post-harvest losses, which is actually true. But very recent study shows that they also have 20 to 30% losses. At what stage? At the consumer state. How? Because people buy and they don't use it. Can you think why they don't use it? For example, you buy a big ketchup bottle, right? And it has a 3-month shelf life, and the 2 people are staying at home. You don't have very large families there, right? And they're not able to finish. So before they finish, the shelf life is over. Or sometimes you go and buy, let's say, 2-liter bottle of Pepsi or Coca-Cola, right? They have shelf life of 6 months. I don't know how much is here, but there is 6 months. So you go buy 5 of them, and then in 6 months you only consume 1 or 2. Then what you do with the other 3? You just throw it, right? So people tend to buy a large quantity of material, even though have very, very long shelf life. They're not able to plan. Sometimes they have not opened and shelf life is gone, and sometimes they open, it is in a fridge, but before they consume, shelf life is gone, even though shelf life is quite long. So for example, people will not buy orange juice of 1-liter bottle and keep in a fridge, and this week, whenever they need a juice, they will drink orange juice. They don't do like this. You go and buy 5 different, you have guava, you have mango, you have orange, all juices are there and all open. And many times you open a fridge and say, oh, I want to drink a juice. So you pick up guava, oh no, I don't like guava. Then say, no. Then you pick up orange, oh no, I don't like orange. And you see all 5 in your board. You just close the door and you don't drink anything. And then after 2, 3, 4 weeks, they'll all expire. So you just throw it. And because food is relatively inexpensive in America compared to developing economy, then people don't think too much while buying the food because this is not very expensive. So you buy, when you're doing the shopping, grocery, you buy whatever you feel like, not what you need. And just bring it at home, and then 30% goes waste out of that. So that's a very, very recent study that people did survey at home, and they went through all the inventory, and then 8 months of survey, many houses all across the US in upper class, middle class, lower class, all level they did, and they come up with that even US. So then I was telling, if that is the case, actually that 30% is much more than what you do 30% here, because here there is a processing, distribution, packaging, everything is included in that, right? Here at least you can assume that you didn't grow 100%, your yield was 70%, you lost 3% at the farm itself. That's not a value-added product, right? So that's the loss we have there.
Sir, what are the advancements or research that is going on in space foods?
So in case of a space food, the requirements are this. They want high calorie density food because, well, they have space limitation. I mean, we go space, but we have the space limitation. The shuttle which will go there, or whatever space vehicle they will have, it is very, very expensive mission, right, going in a space. So they have limited space, so they want high density food, high calorie density, nutrient density food. So in the same amount or volume or mass, they want to pack as high calorie and high nutrient as possible. So that's their one agenda. And then other one is that they do not want to carry a lot of water. So they want to have dehydrated, but the problem is that people don't like dehydrated meat. They want to have beef steak or whatever, fish, like a fresh fish. You don't want to dehydrated fish and then you add water. So they struggle with that how can we dehydrate, and then when we add it, then we would have good quality like fresh fish or fresh meat. So reducing the weight, volume, increasing the calorie density, nutrient density. Packaging is a problem. You don't want small particles because there is no gravity there. So once you open, if it goes into the environment there, and if you don't hold it, then they can get it into your machines, then that's a big safety problem, right? So their package design is such that they kind of suck from the, from the package. So then, not every food can be sucked from package. So they need to keep thinking what way we do the packaging so that we can still, have same kind of a food eating feeling as we have on planet Earth. So they struggle with that as well. I mean, in any water liquid, if it is released because of the surface tension, it just forms this sphere, right? So, I mean, I'm sure in a movie you would have seen that you open a bottle, just throw this water, it forms a sphere, and then just go and sort of catch those water droplets. The swallow is also a problem. Here, gravity acts on us, which many times we do not sort of realize. So we are standing vertical. We don't eat while lying flat on the surface, because then our body has to force food to move from here to here, right? But when we are standing or sitting, then the gravity just takes care of it. But there's no gravity there. So the swallowing, moving that food from mouth to inside, that's also a problem. So they design the viscosity, consistency in a manner that it's easy to sort of move through their digestion system. So like that, they have several challenges. And the recent one, what we know and we are working is the shelf life, Absolutely, they want every food which they are carrying 5 years of shelf life. And also there, when they go in a space, there's a lot of radiation, right? And they want to protect because radiation can, oxidize many food components. So they want to protect their food through packaging or whatever containers they have to avoid any radiation on that. So did you watch movie, what is that Mars movie? Martian, correct. Did you watch that? Well, so the other group, which is the horticulture side, I know some scientists at Purdue University, they have been looking how to grow food on the Mars. So they are working on that. So, and I know some people did work in UC Davis to develop some of the small food processing sort of machinery. So whatever we have now, juice processing, milk processing, or canning, we have very huge machineries, right? Very heavy, because we produce tons and tons here. But in a space only 3-4 people will go, they don't need that level of production from each machine. So they were trying to create in the extrusion system or juice making machines, like from orange, if you want to squeeze out juice, the smaller miniature kind of machine, so that they can carry with them, and if they grow something there, then they can do some food processing in a space. I mean, there's a great part of the world where we don't have 3 meals to eat in a day, and these people keep dreaming about the Mars. So they have different challenges. We, in this part of the world, we have different challenges. Any other question? Well, if not, then thank you very much.